Hello my friends and welcome back to the You Can Do TV channel. The production process at the Focal factory in Saint-Étienne, France, showcases a blend of craftsmanship and advanced technology, emphasizing precision and quality in high-end audio manufacturing. The process begins with driver and diaphragm production, the heart of Focal's renowned speakers and headphones. These components are crafted with extreme precision, utilizing lightweight materials like beryllium for the Utopia line. The creation involves careful application of adhesive in precise amounts, ensuring optimal performance. Skilled technicians assemble components manually, as human precision surpasses automated processes in many delicate operations. Voice coil production follows, where workers assemble and align coils with extreme accuracy. Each coil must meet stringent specifications to maintain audio clarity and performance. During this stage, components are tested and weighed meticulously to ensure uniformity. The next phase involves assembling complete drivers. This process includes mounting diaphragms, voice coils, and magnets. Each assembly undergoes rigorous testing to ensure it meets Focal's high standards. Paired drivers are matched to achieve minimal deviation, ensuring balanced sound output. In the speaker production section, enclosures are assembled using custom materials designed for acoustic excellence. Craftsmen apply finishes and conduct detailed quality checks. Similarly, headphone production involves assembling intricate components like ear cups, headbands, and wiring with precision. Quality control is central to the entire process. Each product undergoes extensive testing, including acoustic measurements, to ensure optimal performance. Paired drivers are matched to within 0.5 decibels to maintain perfect sound balance. The factory also features specialized workshops for unique product lines, including Focal's ultra-high-end offerings. This includes products like the Grand Utopia speakers and flagship headphones, where production steps are even more detailed and exacting. The Focal factory's emphasis on craftsmanship and technological innovation ensures that every product delivers exceptional audio performance. The dedication of the production team, combined with cutting-edge techniques, highlights why Focal remains a leader in the high-end audio industry. The production process at Happy Forgings Limited, based in Ludhiana, Punjab, exemplifies advanced forging and machining capabilities. Established in 1979, the company has evolved into the fourth-largest engineering manufacturer of complex and safety-critical heavy forged components in India. The forging operations include a diverse range of presses such as a 14,000-ton mechanical forging press line, three 8,000-ton lines, one 4,000-ton line, a 2,500-ton forging screw press, a 6-ton pneumatic hammer, and 7 drop hammers ranging from 1.5 to 4.5 tons. This robust setup allows forging of components weighing between 3 kilograms and 250 kilograms. Machining processes at Happy Forgings Limited involve dedicated production lines specializing in crankshaft production, along with the ability to manufacture steering knuckles, differential cases, and other precision components. The annual installed capacity stands at 17,000 metric tons for forging and 46,000 metric tons for machining. The company serves both domestic and international original equipment manufacturers across various sectors, including automotive, farm equipment, off-highway vehicles, and industrial machinery for oil and gas, power generation, and railways. The rotor die casting machine features 4 working stations, automating the process of loading aluminum melt into the tooling. Controlled by a PLC system, it supports 3 injection modes: slow, fast, and secondary. The fast injection flow can be manually adjusted. Equipped with an automatic feeding system, cutting device, and mold unloading mechanism, the machine ensures seamless production. It includes protective pneumatic doors on all sides for operator safety and a water cooling system for consistent operation. Key specifications include a mold clamping force of 1,000 kilonewtons, oil cylinder travel of 480 millimeters, maximum mold opening of 800 millimeters, and injection force of 400 kilonewtons. The motor power ranges from 15 to 4 kilowatts. The machine efficiently produces up to 4 rotors simultaneously if the rotor's outer diameter is within 40 millimeters. Modern technology machinery plays a critical role in the efficient and high-quality production of rotor motors in China. The country, as a leading global manufacturer of electric motors, heavily relies on advanced automated machines to meet the increasing demand for energy-efficient and precision-driven rotor motors. Wave winding machine. It automates the complex wave winding process, ensuring consistent coil formation. High-end machines operate at speeds of up to 800 to 1,200 revolutions per minute, RPM, reducing production time by nearly 40%. Automatic coil winding machine, 8 station. With 8 working stations, this machine allows simultaneous winding of multiple coils, increasing productivity by up to 70%. Servo-controlled models ensure high precision with error margins below 0.1%. Insulation paper inserting machine. This machine ensures precise insertion of insulation paper into stator slots, reducing the risk of short circuits and enhancing motor durability. Advanced models achieve insertion speeds of up to 80 to 120 slots per minute. Servo winding inserting machine. This machine automates the insertion of windings into stator slots, improving accuracy and reducing manual labor by 60%. Middle forming machine. It shapes the coils after insertion, ensuring uniformity. Modern models achieve a forming accuracy of plus or minus 0.02 millimeters, enhancing motor efficiency. Servo double sides lacing machine. This machine secures coil windings with precise lacing, minimizing coil movement. Its automated control reduces cycle times by 50%. Final forming machine. It ensures the final coil structure conforms to precise specifications, enhancing motor performance. With advanced machinery, Chinese manufacturers have achieved production speeds of up to 1,500 rotor motors per hour, cutting production costs by 30% while maintaining quality standards. This technological adoption drives China's dominance in the global motor industry, meeting international demands with speed and precision. The fully automatic motor rotor assembly line is designed for producing various induction motor rotor devices with minimal human intervention. This advanced assembly line automates key production processes such as loading, unloading, shaft insertion, rotor turning, anti-rust oil application, CIR clip assembly, and ball bearing installation. Customized according to specific production procedures, it ensures consistent motor quality while being efficient, user-friendly, and adaptable. Insulation paper inserting machine. This machine inserts insulation paper into the rotor slots. It supports various insulation materials such as DMD, DM, and polyester film. This step is critical for ensuring electrical isolation and preventing short circuits. Rotor winding machine. With insulation paper inserted, the rotor advances to the winding machine. Equipped with a touch screen and PLC control, the machine allows precise parameter adjustments for winding, enhancing operational flexibility. Commutator welding machine. The machine welds both riser and hook type commutators, suitable for DC and universal motors. Its 4 power control methods ensure robust, consistent welds, with all settings adjustable via the touchscreen. Wedge inserting machine. This machine inserts wedges made of materials like DMD, DM, or polyester film. This step secures the windings, ensuring long-lasting motor performance. Commutator turning and deburring. Following wedge insertion, the rotor undergoes commutator turning at 2 stations for maximum efficiency. A burr-removing machine cleans the commutator afterward, ensuring a smooth finish. Rotor testing machine. The assembly line includes a testing station suitable for rotors with up to 72 segments. It performs comprehensive tests, saves data automatically, and allows data retrieval and printing for quality assurance. Ball bearing and worm shaft inserting machines. Finally, ball bearings and worm shafts are inserted. Robotic arms pick up components, ensuring precise positioning. The conveyor system efficiently transfers rotors through each stage, completing the assembly process. By integrating these automated machines, the motor-rotor assembly line achieves high production efficiency, exceptional quality control, and reduced labor dependency, making it an essential system for modern motor manufacturing facilities. The production process at Aqua Group, India's leading pump manufacturer, is a testament to precision engineering and technological excellence. Established in 1956 by Mr. R. Ramaswamy, Aqua Group has grown into a global name with over 2,500 pumps manufactured daily at its state-of-the-art facility in Coimbatore. The journey of every pump begins with innovative design using advanced CAD/CAM technology. Engineers create and refine models, and a 3D printer enables rapid prototyping for testing and enhancement. High-quality materials form the backbone of pumps. The foundry produces 2,400 tons of gray iron, non-ferrous, and stainless steel castings monthly. Induction furnaces ensure precise metal melting, while spectrometer analysis guarantees optimal chemical composition. Complex profiles are achieved using specialized EDM wire cutting machines, and CNC machining ensures precision and consistency. Unlike competitors, the company manufactures crucial motor components in-house. Motor laminations and copper winding wires are produced using high-speed presses, heat treatment, and wire drawing facilities. Automated stator winding machines and trickle impregnation processes enhance insulation resistance, ensuring motor durability. The assembly lines are equipped with the latest technology to ensure seamless integration of components. Hydraulic and electric testing eliminates defects, ensuring every pump meets rigorous quality standards. Micron-level tolerances maintain consistency in performance. The company manufactures a comprehensive range of pumps, from agricultural borewell submersibles to domestic pressure booster pumps. Custom solutions, including solar-powered pumping systems, serve diverse global markets. Painting and drying conveyor ensures pumps receive a flawless finish, enhancing both aesthetics and corrosion resistance. The company operates with a zero-carbon footprint, powered entirely by a 20 megawatts wind farm. Social initiatives include homes for children and the elderly, schools for underprivileged children, and financial aid for life-saving surgeries. Through its advanced manufacturing process, stringent quality control, and unwavering customer focus, Aqua Group continues to set industry benchmarks, ensuring its pumps deliver unmatched reliability and performance worldwide. The CTX Delta 6000 is a premium turn mill complete machining center designed for six-sided complete machining. Its main spindle, paired with an optional counter spindle, supports complex, multi-sided operations in a single setup. The ultra-compact master turn mill spindle allows for efficient tool handling and precise machining. A versatile tool magazine, available as a disc or chain system, ensures flexibility and extended machining autonomy. The machine integrates DMG Mori's Celos, an app-based control and operating system that simplifies production management. Operators benefit from the ErgoLine multi-touch panel featuring Celos and Siemens Synumeric, enabling intuitive control and seamless machine operation. The CTX series excels with 5-axis simultaneous machining, producing perfectly milled surfaces on complex workpieces. Its 360 degrees technology integration supports turning, milling, gear cutting, and grinding. This comprehensive functionality, combined with large tool magazines, automatic tool change, and in-process measurement, enhances productivity and automation compatibility. The CTX series represents state-of-the-art manufacturing, ideal for industries requiring precision and flexibility. Its advanced software features include exclusive DMG Mori technology cycles, offering process optimization and shorter production times. The combination of advanced machining capabilities and integrated automation makes the CTX Delta 6000 a benchmark for modern, efficient manufacturing. The GMW EV motor's stator production line is designed for universal movement and human-centered operation, ensuring efficient and precise stator manufacturing through advanced automation and ergonomic design. The line features servo-controlled systems, professional tooling, and easy-to-operate mechanisms, enabling high-quality production with minimal manual intervention. Horizontal slot cell inserter. The production process begins with the horizontal slot cell inserter. This machine uses a servo-controlled paper feeding system for precise and consistent insulation paper insertion. Its quick delivery mechanism ensures seamless station-to-station transfer, enhancing production speed and reliability. Vertical coil winding machine. Next, the vertical coil winding machine performs high-speed winding with up to 8-wire parallel winding capability. It features a servo-controlled wire clamping system for accurate wire placement and tension control. Coil and wedge inserter. The coil and wedge inserter executes 3 phases of insertion in a single step. Its servo-controlled insertion mechanism ensures precise coil and wedge placement. Professional and experienced tooling design supports customized stator configurations, making the process adaptable and efficient. Hydraulic pre-lacing coil forming machine. The hydraulic pre-lacing coil forming machine uses vertical flip feeding, suitable for medium to large stators. Its separated dimension forming system guarantees accurate coil shaping while maintaining structural integrity. Its easy-to-operate, oriented design simplifies handling and reduces setup time. Double ends lacing machine. The double ends lacing machine features a pick-and-place function, allowing automated transfer between stations. It performs double-end lacing for medium to large stators with an all-servo-controlled system, ensuring precise tension and secure lacing. Hydraulic final coil forming machine. The production line concludes with the hydraulic final coil forming machine, which applies a 3D forming design to shape and compress the coils to final specifications. Its total solution production planning ensures consistent quality, dimensional accuracy, and high production efficiency. The square-can production line is a highly automated, precision-engineered system designed for efficient fabrication of square containers. The process begins with sheet metal roll forming, where flat blanks are progressively shaped into a round cylinder. Next, a seam welding station ensures a continuous, high-integrity weld along the cylinder's longitudinal edges, delivering structural rigidity. Once welded, the cylindrical form undergoes a forming operation utilizing specialized square block shaping dies. This reshapes the round profile into a precise square geometry while maintaining dimensional accuracy. For enhanced durability, edge stamping is performed, creating reinforced corners that provide added strength under load and improve handling performance. Following edge stamping, seaming processes fabricate the lid and bottom edges with precision tooling, ensuring airtight and secure closures. Concurrently, automated units produce and attach the can's lid and bottom components, ensuring perfect alignment and fit for reliable assembly.
This is how racing tires are born. Raw rubber is injected into precision molds under tons of pressure and heat. Each tire cures inside a massive press, locking in its shape and tread. Once cooled and demolded, it's trimmed, inspected, and ready for the track. Grip, speed, and safety, engineered in rubber. Ever held a blade so sharp it feels alive? Here's how that happens. It starts with chromium molybdenum vanadium steel, heated to 1,200 degrees Celsius, then precision forged into shape. A laser cuts the blade, followed by hardening at 1,020 degrees Celsius and tempering at 180 degrees Celsius for that perfect balance of strength and flexibility. Robots grind and polish each edge, while ultrasonic baths remove residue. Handles are riveted and shaped with pinpoint accuracy. Then comes the secret sauce: PC sharpening on wet stones, guided by laser-calculated angles. Each knife is honed, tested, and inspected to meet strict European standards. From molten steel to razor-sharp finish, every step matters. Quality isn't claimed, it's built, one knife at a time. Upset forging is a metal forming process where a heated workpiece is compressed axially, increasing its diameter. It's commonly used to form bolt heads, shafts, and fasteners. Toshiba JSW Power Systems manufactures supercritical steam turbine generators up to 1,000 megawatts in Tamil Nadu, India. The facility features advanced rotor balancing, CNC machining, and VPI insulation for generator coils, ensuring high efficiency, durability, and precision, supporting India's growing energy needs with world-class engineering. A hydrogenerator's power begins with water flowing through penstocks into the scroll case, which surrounds the turbine to deliver steady pressure. Wicket gates, controlled by a governor, adjust the water flow and spin the turbine blades with precision. The rotating shaft, or runner, connects directly to the generator's rotor, where electromagnets create a powerful magnetic field. As the rotor spins inside the stator's copper windings, electricity is produced as three-phase AC power. It's fascinating to see how these components work together, synchronizing every pulse with the grid. Real engineering skill ensures every drop of water is converted into usable, reliable energy. Inspecting 777 X-wing spars at Boeing is next-level engineering. Technicians use ultrasonic waves and water as a conductor to spot hidden flaws. Watching this precision in action is genuinely impressive. Inside the ITER vacuum vessel factory, massive stainless steel sectors are carefully welded and assembled. Each piece stands over 6 meters tall and weighs around 500 tons. Engineers work in spotless clean rooms, performing precise welding and dimensional checks. Watching these giant structures come together, you can't help but admire the scale and technical expertise. Meat Stretch, a cutting-edge robot built for moving boxes in busy warehouses. With its mobile base and advanced vision system, Stretch navigates aisles, lifts heavy boxes, and stacks them precisely on pallets. The robot's long, flexible arm and smart gripper handle boxes of various shapes and sizes. It's exciting to see how robotics like this are transforming warehouse efficiency and making tough jobs safer for people. The 15 HDPE pipe scrap grinder machine efficiently grinds HDPE pipe waste into reusable flakes, heavy-duty motor, and durable construction for continuous industrial operation. Behind every solid ingot is a process that runs hotter than a volcano. At Melting Solutions, aluminum scrap is loaded into a tilting rotary furnace and melted at over 700 degrees Celsius. Impurities are removed through fluxing and dross skimming. Once cleaned, the molten metal is transferred into a holding furnace, ensuring consistent temperature and composition. The casting line kicks in. Molds are sprayed with release agents, aligned under the pouring spout, and filled automatically. Water jets cool the ingots as they solidify, locking in shape and structure. Finally, they're ejected, stacked, and labeled for transport. From scrap to solid, every step is designed for efficiency and purity. Watching metal take shape like this? Just mesmerizing. What powers world champions? It all starts here, with battery chemistry. Active materials are coated onto electrode sheets with extreme consistency, then cut to size. Separators are layered, cells assembled and sealed, then tested for exact tab placement. Barcode matching ensures cell compatibility before wiring, assembly control, and case sealing begin. Each step matters, one flaw, and performance drops. The process ends with labeling and packaging. But the precision behind it? That's what fuels speed. This isn't just battery production, it's race-winning engineering. Some blades are built to fly. This one's built to teach. At Fraunhofer, IWES, engineers craft experimental wind turbine blades to test materials under real manufacturing conditions. It begins with layering glass fiber into the blade shell. Then, the spar cap, the structural spine, is positioned and sealed. Vacuum infusion follows, pulling resin deep into the fibers. Thermal imaging tracks curing in real time. Next, automated glue application bonds blade halves with precision. After baking and cooling, the mold opens to reveal the final blade, ready for testing, analysis, and the next iteration. Welding a vertical joint on massive steel plates? That's serious skill. High-heat arcs fuse the edges, layer by layer. Each pass is followed by grinding, smoothing the weld for strength and fit. It's hot, precise, and surprisingly satisfying to watch. This is how precast concrete drainage pipes are made, from raw materials to ready to ship. Aggregates and cement are mixed at the batching plant, then poured into spinning molds for dense, durable precast drainage pipes. After curing, each product is stored, sorted, and shipped. Clean, consistent, and built to handle pressure, literally. What does it take to build structures that move tons or withstand decades? At Stalcon, it begins with raw steel. Plates and beams are cut, drilled, and welded into massive frames, each one tailored to its final role from overhead cranes to vessel sections. The assembly line handles everything: silos, gangways, exhaust systems, and ferry ramps. After surface treatment and inspection, components are shipped and erected on-site. Watching entire bridges come together, beam by beam, never gets old. Whether it's a power plant or a seaport, every weld counts. This is steel shaped for purpose and built to hold. Industrial, durable, and made to endure. How do you repair a 44-ton hydraulic cylinder the size of a shipping container? Very carefully, and with serious expertise. At Montan Hydraulic, technicians disassemble the steering actuator from a giant bucket wheel excavator. Every part is lifted with cranes, cleaned, and measured down to the micron. Worn seals and surfaces are replaced or remachined. Precision grinding restores exact tolerances before reassembly. The cylinder is tested under pressure to ensure zero leaks and full stroke function. Watching it all come back together is oddly satisfying. This isn't just maintenance, it's heavy-duty surgery. And when you're dealing with machines that carve mountains, failure isn't an option. This is hydraulic repair at a truly massive scale. Grounded and gashed, this ship faced 100 meters of hull damage. In Greece, El Greco's repair crew sprang into action. Over 60 welders, fabricators, and engineers worked around the clock, replacing steel plates, welding seams, and inspecting structure inch by inch. It's not just repair, it's resurrection. Seeing a vessel this size rise again, incredibly satisfying. Think giant rings are cast? Think again. This is how they're forged to exact specs. No molds, no shortcuts, just relentless pressure and precision. The transformation is intense, and every step leaves no room for error. It starts with a glowing hot billet. Heated to forging temperature, the steel is pressed into a thick, round preform using a massive hydraulic press. This isn't just brute force, it's controlled power. The preform is then transferred to the ring rolling mill, where it spins between two rollers. One expanding the diameter, the other shaping the profile. Sparks fly. Steel screams. Precision grows with every rotation. The operator monitors dimensions constantly, adjusting pressure and speed to maintain uniformity. Once it reaches the target size, the ring is cooled, checked for roundness, and sometimes machined further. Watching red-hot metal take perfect form never gets old. These rings may end up deep underground in oil rigs or high above in wind turbines, but everyone begins here, in fire and force. These blades power the world, literally. At PCC Airfoils in Mentor, wax pellets are transformed into ceramic molds through a precise dipping process. Superalloy metals are then poured into those molds, creating airfoils designed for extreme heat. After casting, parts go through grinding, machining, and multi-step inspection, X-rays, penetrant tests, and CMM scans. From wax to turbine, this is investment casting at an industrial scale. You won't believe how much engineering goes into one hydraulic valve. At Kongsberg, it starts with nodular cast iron and ends with micron-level precision. Machining centers equipped with over 1,000 tools shape complex manifolds, while turned spools are hardened and ground to ultra-tight tolerances. Thermal deburring, yes, an actual combustion blast clears residual chips. Surface treatments and pressure tests follow. These valves aren't just made, they're engineered to survive under extreme pressure. This isn't your average boring machine. Karaki's KTB13 means business. Its rigid column and precise spindle bore deep into heavy workpieces with smooth, automated motion. Linear guides ensure accuracy across axes, while the CNC control system enables fine-tuned operations down to microns. Watch how effortlessly it handles steel blocks the size of tables. For complex parts, deep cavities, or perfect alignments, this machine delivers. When precision matters, every cut starts with a setup like this. From perfumes to fire extinguishers, monoblock aluminum aerosol cans are essential in packaging a vast array of products. Their strength, lightweight nature, and seamless design make them ideal for pressurized contents. The production of these cans is a continuous high-speed process driven by precision and automation. At the heart of the XR series aluminum can line is a fully automated system. The process begins with an extrusion press machine that cold forms aluminum slugs into cylindrical bodies in a single stroke. These bodies are then sent to the trimmer-cum-brushing machine to achieve uniform height and surface finish. Next, the cans undergo a spray washing or degreasing stage to ensure a contaminant-free surface. Following this, an internal lacquering machine applies a protective coating, which is cured in a gas-heated lacquer oven. Base coating and multicolor printing, up to 6 or 8 colors are performed next, with a final drying oven securing the designs. Necking machines shape the top of the can to accommodate various closures and valves. Throughout the line, Advanced automation and precision alignment ensure stability and quality. All machines are integrated with Siemens PLCs, featuring color touchscreen interfaces that display live production data. The entire system allows seamless transition between stages, ensuring efficiency, energy savings. The DA360S shear system by KRRASS demonstrates high-precision cutting of 25 mm thick metal plates. With hydraulic power and synchronized blade clearance adjustment, the system ensures clean, accurate cuts. The intuitive DA360S controller enables programmable settings, boosting efficiency for industrial-grade metal fabrication tasks. Tank manufacturing machines are specialized equipment designed to produce plastic tanks ranging from 60 to 10,000 liters with 1 to 6 layer configurations, including optional foam insulation layers. The process involves melting raw plastic material and forming the tanks using rotational molding technology. Plastic materials are melted, injected, and shaped using blow molding technology. The entire system is controlled via a PLC, ensuring automation, precise quality control, and efficient energy usage throughout the production process. Advanced Spiral Technologies' True Helix flight forming system allows anyone to form large screw flights up to 48-inch outer diameter, 48-inch pitch with precision and ease. No prior experience is required. The system uses intelligent software and PLC-controlled machines to ensure consistent repeatability. Every flight is formed to the exact specifications, delivering perfect helix geometry, uniform size, and high-quality results, efficiently and reliably. The IMT 1607 BOL-DRINI Ribo 32 is a high-performance flanging machine designed for hot flanging applications. Equipped with a heat protection liner, it ensures structural integrity during high-temperature forming of large-diameter heads and dished ends. The machine enables precise flanging of thick-walled components with excellent repeatability. Its robust hydraulic system, programmable controls, and adjustable forming speeds allow for optimal shaping under heat. Suitable for pressure vessels and heavy-duty tanks, the Boldrini Ribo 32 delivers efficiency, accuracy, and durability in demanding industrial environments. QSC Forge specializes in the production of high-quality rolled rings, used extensively in aerospace, power generation, and industrial applications. The manufacturing process begins with heating a metal billet, typically made of carbon, alloy, or stainless steel, to a high temperature in a forge furnace. At QSC Forge, the critical step in producing high-performance rolled rings is the ring rolling process, where radial axial ring, which simultaneously compresses the ring radially, reducing wall thickness, and expands it axially, increasing the diameter. The machine is equipped with CNC control systems to ensure precise adjustment of rolling forces, rotation speed, and ring geometry. The rolling process also allows for tight tolerances, minimal material waste, and uniform mechanical properties throughout the ring. This precision forming technique enables QSC Forge to produce rings up to several meters in diameter for demanding applications. The hot rolling mill process begins by heating steel slabs to around 1,200 degrees Celsius in walking beam furnaces. This step ensures optimal metallurgical properties by dissolving carbides and nitrates. The heated slab then undergoes high-pressure descaling to remove surface oxides. In the roughing mill, a powerful 4-high rolling system reduces the slab thickness from 22 centimeters to about 3 centimeters in several passes. The processed slab, now called a transfer bar, is coiled for temperature equalization. It then enters the finishing mill, where it's further reduced to 1.8 to 16 millimeters. Precise control of profile, flatness, and cooling rate ensures the final coil meets strict mechanical and dimensional specifications. Offshore pipeline construction typically takes place on a lay barge, where 18-meter pipe sections are welded and inspected before submersion. After welding, the weld area undergoes automated ultrasonic testing, AUT. A steel guide band is wrapped around the pipe to guide the scanner. The pipe surface is cleaned and sprayed with soapy water to reduce surface tension, allowing proper contact. The scanner circles the weld area, sending real-time data to a remote operator station for evaluation. Each scan cycle lasts about 3 minutes. Calibration ensures accuracy. Once verified, the weld is cleaned, insulated, and coated to protect against harsh marine environments before the pipe exits the barge into the sea. The A2 Belchen Tunnel renovation project in Switzerland is a major engineering effort designed to upgrade 2 aging tunnel tubes without disrupting the busy A2 highway. To achieve this, a new 3.2 kilometers tunnel, called the Saneringstunnel, is being constructed using the largest tunnel boring machine, TBM, ever used in the country, with a cutting diameter of 14 meters. As the TBM advances, it installs precast concrete segments known as tubbing, forming the tunnel lining. These segments allow for precise adjustments in tunnel direction, both horizontally and vertically, enabling the machine to navigate complex curves. Around 550,000 cubic meters of rock are excavated and partially reused. The rest is transported by conveyor belt to an off-site landfill. The tunnel's internal structure is built in stages, including waterproofing membranes, reinforced concrete arches, and a utility channel beneath the roadway. Strict logistics ensure that one truck can enter or exit the site every minute at peak times. After construction, advanced safety and ventilation systems are installed and tested, preparing the tunnel for future use. Once the new tunnel is operational, traffic will be diverted, allowing the original tunnels to be fully refurbished. ABB's Azipod is a gearless electric propulsion system that integrates motor and propeller in a steerable pod. It delivers 360 degrees thrust, reduces fuel consumption, and improves maneuverability. The new mid-power model is optimized for ferries, helping meet emission targets with significant energy and carbon dioxide savings. Delicate, elegant, and crafted by hand. This is how a Riedel sommelier's wine glass comes to life. It all starts with molten glass, drawn from a furnace at over 1,200 degrees Celsius. A master glass blower gathers the glowing material onto a blowpipe, turning and inflating it with practiced breath. The bowl takes shape in seconds, guided only by instinct, muscle memory, and a steady hand. No molds, no shortcuts. Once the bowl is formed, a second artisan attaches the stem, fusing both parts in a single fluid motion. Timing here is everything. The glass must be hot enough to merge, but stable enough to hold its shape. The foot is then pressed onto the base and reheated to ensure perfect symmetry. While still warm, the glass is spun on a graphite pad to smooth the connection points and ensure balance. Each glass is returned to the flame for subtle refinements. A flick of the wrist stretches, trims, or balances the piece before it's slowly cooled in an annealing oven. The cooling process can take hours, preventing stress fractures and preserving strength. Finally, each glass is inspected under bright lights. Any imperfection means it doesn't make the cut. Riedel Sommelier series is not just drinkware, it's tradition, breath, and fire transformed into something timeless. Watching it made reminds us, even in a world of automation, some things still require the human touch. From ancient elegance to modern dining, porcelain remains timeless. But how is it made today on an industrial scale? It starts with raw materials like kaolin, feldspar, and quartz, combined into a powder blend. This mix undergoes refining, including magnetic separation and screening, to eliminate impurities. Water is added, forming a smooth slurry that's filtered, vacuum dehydrated, and stored in aging silos. Next comes shaping. Automated pressing machines and molding systems give each item its basic form: plates, bowls, or cups. Each form is visually inspected to ensure consistent shape and thickness before moving forward. These shapes are then trimmed, dried, and prepared for glazing. Glazing isn't just for aesthetics. It improves durability and water resistance. A fine layer of glaze is applied by dipping or spraying. The glossy coat needs to dry before firing. Firing is intense. Kilns reach over 1,300 degrees Celsius, transforming clay into vitrified porcelain. The glow inside the furnace looks like something from another world. Once cooled, the products are unloaded, graded for quality, and checked for cracks or deformities. Selected pieces are stamped with the company's mark, then sent for a second low-temperature baking to fix the stamp. Finally, after inspection, each item is carefully packaged for delivery. ITER. It's a delicate balance of chemistry, craftsmanship, and heat. And somehow, every cup still feels personal. Oval ducting, sleek, efficient, and often hidden behind walls or ceilings. But shaping flat steel into this aerodynamic form takes more than just force. It takes engineering. It begins with feeding coiled sheet metal into a line of forming rollers. Step by step, the flat strip bends into a circular tube. A spiral lock seam is created during the roll-forming stage to hold the shape tight. Next, a hydraulic press flattens the round tube into an oval profile. It's oddly satisfying to watch the perfect symmetry emerge under pressure. Cutting units then size each duct precisely. Some machines add reinforcements or flanges, depending on installation needs. The process may look simple, but the tolerances are tight. These ducts must perform reliably in real-world HVAC systems. From roll to oval, precision matters at every step. What does it take to make a rope that holds steady through salt, strain, and storms? At Samson, it begins with high-performance fibers, Dyneema, Technora, Vectron, tested before even entering production. Twisters spin them into yarns, then into strands. These strands are braided into ropes with torque-free balance, ensuring they won't unravel under pressure. Coatings are added for UV resistance and strength. Finally, expert hands splice eyes, attach thimbles, and finish each product to exact specs. From fiber to finish, every step is built on control, endurance, and trust. What goes into making a product designed for both safety and pleasure? At Manforce, the journey from liquid latex to a premium condom is a blend of science, precision, and trust. Raw latex sourced from southern India is stabilized with carefully measured compounds. It's filtered, tested, and pumped into massive steel tanks, ready for transformation. Here, glass molds are dipped into the latex, forming the base shape of each condom. As they emerge, the condoms are beaded and baked to set their shape. Then comes a leach bath and a water jet to release them from molds. Visually, it's mesmerizing, but this is only the beginning. The molds move through a series of ovens, where controlled heat gradually cures the latex, giving it strength and elasticity. Each piece is washed, dried, then coated with a special powder to prevent sticking. After a cool-down period, every unit undergoes electronic testing. 5 lakh pieces per batch are scanned for microscopic holes using high-voltage electrodes. Failures are instantly rejected. To ensure machines are working correctly, each test line runs control samples with tiny artificial defects. If the line misses a defect, everything is flagged. No compromise is allowed. Selected condoms go through additional burst and water leak tests. Watching a condom inflate like a balloon until it bursts is oddly satisfying and reassuring. Each one must meet strict parameters for expansion volume and burst pressure. Even minor inconsistencies mean the batch is pulled for reevaluation. Flavoring adds the final signature. Strawberry, chocolate, vanilla. Each flavor is mixed with silicone oil, then dosed onto the condoms via automated machines. These are heat-sealed into foil wrappers, manually inspected for closure and integrity. Lubricant content is checked post-wrapping using ultrasonic alcohol baths. Only when every standard is met does the batch proceed to packaging. From plant floors staffed largely by women to solar-powered roofs, sustainability is baked into every layer of this operation. Conveyor lines load inner boxes into cartons, ready for shipment across the country and beyond. Every step in this process protects something essential: trust, intimacy, and health. Cracking an engine block in seconds? The Nye EBC200 makes it possible. Its powerful jaws crush aluminum housings and iron components into fragments. Steel and aluminum can then be magnetically sorted. No massive shredder needed. It's brutal, efficient, and strangely satisfying to watch. How do you control the flow of an entire waterway, down to the millimeter? At ITER, it starts with installing a massive new sluice chain, a critical component that lifts and lowers the gate to control water flow. Specialized teams begin by removing the old chain, section by section. Precision is key here. Even millimeter deviations can disrupt the entire mechanism. The new chain arrives in massive coils and is carefully unwound, aligned, and mounted on the gate structure. Hydraulic lifts, alignment tools, and guide rails help position each link perfectly. The process demands patience, strength, and an eye for detail. Final tensioning ensures the chain operates smoothly as the lock opens and closes. It's more than just steel. It's timing, resistance, and fluid control. You might not see it, but every ship passing through owes its safe passage to this chain. Deep inside hardened die steel, a vibration-damping boring bar carves out the inner diameter with precision. Using a TAC 950 lathe, it shapes a 990 mm cavity. Steady, controlled, and oddly hypnotic to watch. One wrong move and it's scrap. But the CP6000 doesn't flinch. This 5-axis machining center takes on a microscope housing, an intricate part with tight tolerances and complex geometry. The part rotates and tilts effortlessly as tools slice, mill, and drill from every angle. Watching each surface take shape feels like engineering choreography. One mistake, and the entire piece is scrap. But here, every pass is deliberate. From roughing to finishing, the process reflects a perfect balance between machine power and micrometer-level control. Beautiful and brutal, just like high-end manufacturing should be. They don't just build pressure, they carry the weight of entire machines. Here's the hidden precision behind Eaton's manufacturing. It all starts in a clean room assembly area. Machine casings are inspected, cleaned, and staged. Technicians slot in pistons, swash plates, and valve blocks, each measured down to microns. It's like assembling a jigsaw puzzle in an environment silent enough that even a dropped part echoes. Next, components progress to precision alignment. Shafts are installed and rotated to test friction and resistance. Any roughness triggers an immediate rework. But first, all parts must pass initial fit checks. Trial assemblies ensure tolerances align before final locking. It's a quiet moment where errors reveal themselves early. Once alignment is confirmed, dynamic balancing is done to prevent vibration at high RPM. A few grams off-center? Unacceptable. After that, sealing comes next. O-rings, gaskets, and pressure seals are fitted with exact torque. A single misaligned seal could spell disaster in the field. That sense of this part better never leak. You can feel it in the air. Then comes flushing. Residual debris from machining is purged using high-pressure fluid to prevent contamination down the line. It's a hidden step but critical for long-term reliability. Sun pumps go into hydrostatic test rigs. Pressurized oil forces out any hidden defects. Leaks, noise, or pressure drop. It fails. The pass rate? Relentless. Engineering isn't just theory. It's brutal, real-world validation. Before calibration, thermal cycling simulates real-world heat expansion. Some pumps get warm under load. This step ensures they still hold pressure after heat stress. Nothing leaves here untested. Successful units get a final stage of calibration. Flow rate, pressure thresholds, and torque resistance are dialed in. Results are logged, serialized, and traced. Every pump carries its own performance fingerprint. And after all that, they rarely make a sound, but they move tons of load without flinch. From red earth to razor-sharp resolution, this is how a printing plate comes to life. It starts with bauxite, mined near the equator. From 2 tons of ore, just 1 ton of alumina is refined. Then comes smelting. At 700 degrees Celsius, pure aluminum is extracted via electrolysis and cast into 30-ton ingots. Hot rolling flattens these giants into coils 2.4 kilometers long and just 4 millimeters thick. Impressive, right? After cooling, they undergo cold rolling, thinning down to 0.15 to 0.3 millimeters depending on the application. Now it gets precise. At the coating plant, each coil is etched, grained, and cleaned. Next, a light sensitive coating is applied. This is where printing magic begins. Every plate is laser inspected. Flaws get rejected instantly. Nothing escapes quality control. They're then trimmed, covered with a protective sheet, and sealed in light, tight packaging. Flawless aluminum becomes a high-performance canvas. And all of it, from mining to microscopic coating, is done so your prints never miss a detail. A Michelin Tweel, retreaded and rolling again. This isn't your everyday tire. The Tweel ditches compressed air in favor of high-strength poly-resin spokes. No flats, no inflation, just durability. But retreading it? That's a whole different challenge. Pete's Tire Barn stepped up. It begins with buffing. High-speed grinders strip off the old tread, exposing the raw base. Every spoke edge is protected during grinding to avoid heat damage. Technicians then fill gaps with bonding rubber, smoothing the surface into a uniform foundation. The rubber is spread in multiple passes, ensuring no gaps between spoke ends and outer casing. Next, the surface is inspected under strong light to verify consistency. Any uneven areas are reworked immediately before moving on. The entire surface is then brushed with a bonding adhesive, sticky and evenly spread, to ensure full contact with the new tread. The glue is checked for tackiness before moving forward. Too dry, and it compromises bonding. Any excess is wiped from the sidewalls to avoid contact with curing molds. Now the Tweel is ready to receive its new tread. A fresh tread is wrapped snugly around the Tweel. No shortcuts, just full contact, edge to edge. A guiding rail system helps align the tread perfectly to the rotation path. Then comes enveloping. The whole tire is sealed in a black rubber sleeve, clamped between heavy metal plates. The sleeve is stretched into place manually, checked for wrinkles before pressing. Before curing, air is removed. The sleeve is vacuum sealed to pull the rubber tightly against the tread, eliminating voids or bubbles. The entire assembly is then placed into a curing chamber. Over 4 hours of heat and pressure fuse the new tread to the structure. A timer is set, but temperature and pressure are constantly monitored and logged. If the pressure drops mid-cycle, the batch is flagged for inspection. Once cooled, it's removed and only then is air pumped in. The inflation helps release the tight rubber sleeve without damaging the retreaded surface. After inflation, the casing is manually pulled off, firmly but carefully. What's left is a second-life Tweel, reliable, durable, and ready for real-world abuse. Building an aircraft bulkhead isn't just about strength. It's about precision, scale, and automation. At over 5 meters wide, this carbon fiber composite structure is formed layer by layer using advanced robotic systems. It begins with rolling machines laying structural plies directly onto a double-curved mold. Each sheet conforms precisely to the geometry. Then come reinforcing patches, cut by CNC machines and picked up by a modular gripper with 127 suction modules. These modules adjust dynamically, draping each piece onto the mold with millimeter accuracy. Optical sensors and fiber-angle cameras verify placement, because even a small misalignment could compromise structural integrity. Co-working robots then lay longer plies, calculating collision-free paths to avoid interference. Next, stiffening stringers are installed using vacuum grippers. Auxiliary material packages are added and sealed with epoxy resin. Vacuum bagging follows. Semi-permeable membranes are placed and sealed around the part before pressure is applied evenly using a multi-kinematic gripper. Finally, RTM epoxy resin infiltrates the dry fibers. After curing in a controlled oven, the part emerges lightweight, rigid, and aerospace ready. This is automation pushing the edge of composite manufacturing. This isn't just bodywork, it's structural correction at its core. In this video, we dive into how the UL300 collision repair system transforms a misaligned vehicle frame back to factory spec. Before anything gets pulled or straightened, the repair bench itself must be locked down. Technicians bolt the UL300 firmly to the shop floor. Stability is everything. When tons of force are involved, nothing can shift. A pneumatic airbag jack lifts the vehicle slightly, just enough to slide the bench rails underneath. The main beam is then aligned and fastened to the base structure. With the rails in place, roller supports and positioning clamps are locked down one by one. Once in position, clamps secure the wheels and underbody to turn the car into a fixed reference point. At the front, a pulling tower is chained to the deformed section. This isn't brute force. It's calculated restoration. A hydraulic pump applies tension slowly, pulling the frame into alignment. Every shift is monitored with laser tools or mechanical gauges. If damage extends diagonally, synchronized side pulls are used. Safety locks are engaged throughout, preventing unexpected movement. When all dimensions check out, chains are removed and the pulling tower is retracted. The process demonstrated here shows exactly how the UL300 would restore a misaligned frame to precise factory specs and ready for body panels or paint prep. Precision isn't optional in structural repair. It's everything.